Okay, hi everyone. So let's get started. Hope you're still doing okay as we head toward the end of the semester. Just 2 lectures after today. So the topic of today's lecture is greedy algorithms. And it's a very general technique, just like divide and conquer and dynamic programming, which we've already covered in this module. So greedy algorithms is about recasting the problem so that there's only one subproblem that needs to be solved at each step. So remember that dynamic programming, we try different subproblems, right? So like knapsack, we try whether to include the item n or not, or like longest common subsequence, we try whether to exclude the last character of the first sequence or the last character of the second sequence. So we try different options and see what's the best option. But the greedy algorithms is going to be a framework where we only need to try one subproblem. So at each step, we go down one route, not different routes, not several routes, right? So it beats divide and conquer and dynamic programming when it works. And this when it works is in bold because many times it doesn't work, right? So, but when it works, it's great. And even sometimes, as you'll see, so in one problem, there could be many ways to do greedy. There could be many different greedy algorithms, and some might work better than others. So it could be that some greedy approach works, whereas others don't, even in the same problem. So you have to be careful about what, how you apply this method. Okay, so let's look at the first example, and that's a fractional knapsack. So we've seen the knapsack problem in the last lecture. Right? Remember, that's the problem where we have a set of items, right? A bunch of items, each item with a weight and a value, and then we have the total capacity of the knapsack. And what we want to do is we want to fit in as many items as possible, not as many items as possible, so get as much value as possible subject to the capacity, right? The sum of the weights of the items that you choose should not exceed the capacity of the knapsack. And we saw that there's a dynamic programming algorithm for this problem, where at each step we decide whether to include an item or not, and then we look at the remaining items. So for fractional knapsacks, they're similar, except that now for each item, the choice is not just between whether to include it or not, but you can also choose to include any fraction of it that you want. And say if you include the half of an item, then you also get the half of its value, right? Like for this top left item, it's worth $100 and it has the capacity, it has a weight of 1 kilogram. So you could choose to include, say, 0.6 kilogram of this item and you'll get the value of $60. So you can choose any fraction of an item that you want. Okay, so and the goal is again that we want to maximize the value that fits in the knapsack. So the input is the same as for the original knapsack, right? W1, V1, that's the weight and value of item 1, and so on up to item n. And then capital W, that's the capacity of the knapsack. And we want to output now the weight, so x1 through xn, that's how much of each item you choose to include in the knapsack. And you want to maximize the total value, right? So the total value is calculated as sum, right? This I goes from 1 to n, and then it's vi, so that's the value of the entire item I, and then you scale it, right, according to how much of this item you include, right? And that scaling is by multiplying it by xi over wi. So if you include none of this item, if xi equals 0, then that value is 0. If you include the whole of this item, that's xi equal wi. That's in that case, you get the whole value of vi. You include half of this item, you choose xi being half of wi, you'll get the value of half of vi from this item, and so on. And the constraint is again that the total weight that you include should not exceed the capacity of the knapsack. So that sum of xi does not exceed the capital W. And also the weight that you include from each item, of course, should not exceed the total item, right? You cannot, if this item is 1 kilogram, you cannot choose to include like 2 kilograms of this item. So 0 is xj is between 0 and wj for every j between 1 and n. So that's the specification of the problem. And for example, in this case, you might choose to include the whole of the top left item, so the whole 1 kilogram. That's going to give you a value of $100. And on the bottom left item, right, it's 5-kilogram item, maybe you choose to include just 3 of them, because that's already everything that fits into the knapsack. You can only include 3 kilograms of this item, so you get a value of $60. Right? That's the proportion of the value, 3/5 times 100. Okay, so yeah, just like in dynamic programming, so in greedy algorithm, like one component of it is the optimal substructure, right? So this says that if you remove, in this case, if you remove, say, little w kilograms of one item from the optimal knapsack, right? So suppose you have some optimal knapsack already, some optimal choice, and the optimal substructure says that if we remove like some number of kilograms of one item, it might not be the whole item, right? Maybe from item J, like currently in the optimal solution, item J has like 1 kilogram in it, and maybe you choose to remove, say, like 0.6 kilogram of item J, then the remaining load must still be the optimal knapsack of the remaining items, right? So once you remove like this little w kilograms of item J, then the capacity that you have left is capital W minus little w, right? And the remaining items, so what you have the other n-1 original items, right? These are still there. And the item J, you've removed the little w of this item. So the remaining weight of this item is Wj minus little w, right? And this claim is saying that, okay, if you have an optimal solution, you remove some portion, could be the whole of this item, could be like part of this item J, then in the remaining instance, like you must still have an optimal solution. So this is just like optimal substructure in the previous lecture with the original knapsack, right? There you remove a whole item. Here you also allow to remove the part of an item. And so the proof is similar, right? It's again like this cut and paste argument. So yeah, I think you can look at this yourself, but I mean the idea is essentially the same, right? That it's all cut and paste is always about you remove, like suppose what you remove, and then like you remove something, and then in the reduced instance you don't have an optimal solution. There's something that's better. Then with that something better, then you paste like what you removed back in. It would be a better solution of the original problem. And so this is what it's saying here. Yeah, so you combine like this what we removed back into like what the original kind of the optimal solution of the reduced instance, then you'll get a better solution to the original problem, and that would be a contradiction. Okay, so now in the integral knapsack problem, right, we use this optimal substructure to decide whether to add item J or not. Right, we try both cases: add item J, not add item J, see what's better. But for fractional knapsack, we can do better, right? How? So you can make a guess. So suppose you don't know anything about algorithm design and would like to solve this problem, right? You face this fractional knapsack problem in real life. So what strategy would you use? Right? Would you first take the item with the maximum value, then the item with second maximum value, and so on until you exceed the weight where the last item could be fractional? Or would you first take the item with minimum weight, then second minimum weight, and so on until you exceed the weight? Or would you take the item with maximum value per weight, second maximum value per weight, and so on until you exceed the weight? So in all these cases, the last chosen item could be fractional because you want to fill in the knapsack to the fullest, right? Because there's no point in with a fractional knapsack problem. There's never any point, right? Never any use in leaving part of the knapsack empty. You always want to fill in the knapsack to its full capacity. Okay, so which choice do you think would be the best? Yeah, so everyone's getting this right. So it's choice 3, right? You want to maximize you choose the item with the maximum value per weight ratio. So that's also sometimes known as bang per buck. Kind of the per amount of money that you spend, you want to maximize the value that you get in return, right? So because the first choice would ignore the weight, right? So you choose like you maximize the value, but maybe like the item with the maximum value is really, really heavy, even though it has large value, like you have to spend like too much weight. And the second choice, you try to choose an item with minimum weight. I mean, that's kind of, again, a good thing, having minimum small weight, but maybe the small weight come with value 0. That's completely useless, right? Even though this item has weight only like 1 gram, but its value it has value 0. Like why would you even choose to include it, right? You should throw this item away. So looking at the value alone or looking at the weight alone does not work. You have to combine the two, and the way to combine it is to look at the ratio, right? So the maximum value per weight, right? What kind of per kilogram, how much value do you get back in return? And this is going to be the right choice for a fractional knapsack. Now note that all these 3 choices, they describe greedy approaches, right? These are greedy algorithms, all of them, but only one of them work, right? If you just greedy with respect to value, it doesn't work, doesn't always work. You greedy with respect to just weight, you try to minimize the weight, again, like doesn't always work. So, even if you know that you want to use a greedy approach, you still have to be careful with what greedy approach, right? What you use this approach on? What's the objective that you want to maximize or minimize, kind of in each of your choices in the greedy algorithm? And yeah, so this is the greedy algorithm that we want to use. And in order to prove that this actually works, that this greedy algorithm gives you the optimal solution, right? The important component is what's known as greedy choice property. So this is going to be on top of the optimal substructure, right? Remember, for dynamic programming, you only have this optimal substructure, but for greedy, you also need to prove a greedy choice property. So that essentially says that when you make a greedy choice, it's kind of the right choice, right? It doesn't hurt to make this choice. So in this case, right, suppose J star is an item with the maximum value per weight, right? Value per kilogram. So that's Vj divided by Wj. Then this greedy choice property says that there exists an optimal knapsack that contains the minimum of Wj star and capital W kilograms of item J. Now, okay, this expression minimum might be a bit confusing at first, but okay, so what's going on here? This minimum, right? So there are 2 cases, right? Have a minimum of 2 quantities. It could be that Wj star is at most capital W, then this quantity would be Wj star, right? So what this is saying is that this capital W, so there's enough capacity to fit in the whole item J star. Right? In that case, you can afford to fit in the whole item. So choose whole item J star. And the other case is that Wj star is greater than capital W, right? In that case, this minimum would be capital W. So in this case, what's going on is that there's not enough capacity even to fit in this whole item J star alone. Right. In this case, what you want to do is that you want to fit in as much as possible, right? And then you're done because the knapsack is already full. So in this case, choose weight W, right, of item J star. So that's why we take the min of the 2 quantities, right? We want to choose as much of this item as possible. If we can choose the whole item, great, but maybe we cannot. If we cannot, we can only choose up to the capacity that we have. So that's why we take the minimum of these 2 quantities. Okay. So why does this work? Right? We need to prove that that this actually works. So that there is an optimal knapsack that contains like this quantity, right, as much as possible of item J star. Okay, so let's look at the optimal knapsack. Right? Suppose it contains like x1 kilogram of item 1, x2 kilogram of item 2, and so on. And the sum of these xi's is the minimum of Wj star and capital W. Right? So this is the amount that we are intending to give to just item J star. But suppose like this amount is being used also for other items, right? Using it to choose some weight of item 1, some weight of item 2, and so on. So what we claim is that actually it doesn't hurt to replace this weight by just item J star, right? Why not give this like whole space to item J star? And the point here is that the total weight would not change, right? Because we're fitting in the same amount of weight. And also the total value would not decrease, because if you replace, say, like x1 kilogram of item 1 with x1 kilogram of item j star, because item j star has the maximum value per kilogram, your value would never decrease, right? Because kind of you're looking at the same weight between item 1 and item j star. What item would give you more value has to be item j star, or at least not less value, right, than item 1, also not less value than item 2, and so on. So we can afford to replace all these items, all these other items, by the same amount, same weight of item j star, right? So the knapsack would stay optimal. So this is why we can without loss of generality, right, we can spend this much amount, right, spend this much weight on just items j star alone, right, to give this weight to item j star. So this is our greedy choice property, right? So once we have this, we already have a strategy for the greedy algorithm, right? So what we can do is we look at this item j star, which maximizes the bang per buck, right? So the value per weight, and we put as much of this item into the knapsack as possible, right? And if the knapsack already weighs capital W kilogram, we're done, right? The knapsack is full. Well, otherwise, we just look at the remaining problem, right? We use the optimal substructure to solve the subproblem, where the whole of item j star is removed and the knapsack weight limit is reduced by W of j star, right? By the weight of item j star. So you can see that here we're only considering one subproblem, right? We fill in as much of item j star as possible, then we look at the remaining instance. It's just one subproblem that we care about. And we know that we only need to focus on this subproblem because there's always an optimal solution that puts in as much item j star as possible. Okay, so this gives us this greedy algorithm, right? So what we do is we sort the items, right, according to the value per weight, and we go from maximum value per weight to minimum, and we fit in, right, for the next upcoming item, we fit in as much of it as possible. If there's space left, we go to the next item, and so on until we run out of space, right? So this gives us this the whole algorithm, very simple. So yeah, you see that because in the first stage we have to sort, right? So that's going to take time n log n, and then in the remaining stage, right, we just go item per item, right, from the maximum bang per buck to minimum, and then we stop whenever the knapsack is full. So that this for loop is going to take time just order n, and so the total time that it takes is order of n log n, right? So this is your greedy algorithm. And by the way, so this right, so this greedy algorithm, I mean, you could also imagine using it for the original knapsack problem. I mean, you could also do this, right? You sort the items according to value per weight, and then like you go from maximum to minimum, and then stop whenever the knapsack is, well, the knapsack might not be full, right? But maybe like you can no longer fit in the next item, something like this. So this also gives a greedy algorithm, right? But the thing is with the original knapsack, right, the non-fractional knapsack, yeah, it's not a bad idea actually, but it's not always going to give you the optimal solution. So you can try to come up with an example where this algorithm is not optimal for the original knapsack problem. That's a nice exercise. But for the fractional knapsack problem, kind of because you can fit in any fraction of any item, you can fill in the whole knapsack. It's always a good idea to like go from maximum to minimum bang per buck. Whereas for the original one, because it's you have to choose the whole item or not. Sometimes it could be like some item has good value per weight, but maybe it's like too large, and it would be better to use that space to fill in like smaller items, even though like it gives you less value or even less value per weight, so something like that. So you see that these two problems, like fractional and non-fractional knapsack, even though they look very similar, so the greedy algorithm works only for one of them, only for the fractional version. Okay, so this is an example of the paradigm for greedy algorithms. So what we do is, so first we cast a problem where we have to make a choice, and we're only left with just one subproblem to solve. Right? We prove that there's always an optimal solution to the original problem that makes the greedy choice. So it's safe to make the greedy choice. Right? It's kind of without loss of generality, we can make this choice because we're not going to lose anything by making the greedy choice. So this we have to prove. This is the greedy choice property. And then finally, we use the optimal substructure. So this part is similar to dynamic programming. We use optimal substructure to show that we can combine an optimal solution to the subproblem with the greedy choice to get an optimal solution to the original problem. So we can just focus on solving the subproblem and getting the optimal solution to that. So that gives us the paradigm for greedy algorithms. Okay, so let's look at an even simpler example of a greedy algorithm. This is probably the simplest kind of greedy problem you can imagine. So suppose that you're given n items with the positive weights W1 through Wn. You want to find a set S of k items that maximizes the total weight of the items in S. Right, so what are you going to do? Well, so you cannot take all because you can only choose k out of the n items. Yeah, so exactly I mean, like this should be quite clear, right? Which k are you going to take? If you just care about the sum, then you're just going to take the highest k items, right? The k items with the highest weights. But okay, let me go through this in detail anyway to demonstrate how the how like the components, the elements of a greedy algorithm. So what's the optimal substructure here? Right. So the optimal substructure is, suppose you're looking at any optimal solution of this problem, and it contains item I. Right. So we claim that if we remove item I from this optimal solution, then S minus I, so the optimal solution minus item I, is still optimal for the subproblem with the ith item removed, and the size limit goes down by 1. Right. So this is similar to what we just did for the fractional knapsack. So it's a cut and paste proof. Right? So if T is optimal for the subproblem and it weighs more than S minus I, then you use that and then put item I back in would weigh more than S. That would be a contradiction. And the greedy choice property here is that we want to claim that it doesn't hurt, like at any stage, it doesn't hurt to choose the maximum weight item. Right? It never hurts. And that we say, suppose the ith item has a maximum weight. So we claim that there is an optimal solution that contains item I, right? Why is that? Well, suppose there's an optimal solution that doesn't contain item I, then we can just replace any item in the optimal solution with item I, right? The total weight would not decrease, and it's still a set of the same number of items, like k items. So the new set would still be optimal, and now it contains item I. Right, so this shows that there exists an optimal solution that contains item I, so it doesn't hurt to take item I. Right, it cannot hurt you, cannot come back and hurt you later by taking item I. Oh, I think I accidentally unshared the screen. Let me share again. Okay. Yeah, so this gives us the greedy algorithm, right? So I'll put the top k heaviest items, and the correctness. Yeah, I mean, again, this is kind of really like elaborating on the details where the algorithm, the correctness and everything is quite obvious. But okay, so by the greedy choice property, we can assume that the heaviest item is in S, right? We can take the heaviest item, and then we use the optimal substructure, so we can combine this heaviest item with the solution to the remaining subproblem. So then what this algorithm does is it takes the k heaviest items one by one. So you can sort everything, but because you only need the top k, right? You don't need to really sort, kind of don't know the order of this top k. You can also determine just the k's heaviest item, and then like look at everything that's heavier than that. Okay, the point here is that we can use a greedy algorithm. Okay, so any questions so far before I move on to the next example? Okay, so right. So for the next example, we're going to look at the graphs. So we haven't talked that much about graphs in this module, but this example is about graphs. So it's about minimum spanning trees. So the input of this problem is a connected undirected graph, right? It has a weight function, so that's each edge has some positive real number weight. And for simplicity, let's just assume that all edge weights are distinct. Right, so in CLRS, like they also treat kind of the general case where some edge weights are the same, but that's not really the interesting point. Let's assume that all edge weights are distinct, and what we want to output is a spanning tree. Right, so what's that? So that's a tree that connects all vertices, and this tree has minimum weight among all trees that connects all vertices, right? So we just sum up the weights of the edges in this tree. So for example, like you take this graph, right? So what's a minimum spanning tree? Can someone like output, maybe the edge weights of a minimum spanning tree? Yeah, I think someone is drawing on the slide. That's good. Yeah, so essentially, I mean, if you think about this, I mean, there are some like heuristics you can use, right? So first of all, like the two vertices on the right, like because they're leaf vertices, right? They're connected to only one edge. I mean, we have to include them no matter what, right? This 9 and 15 edges, and then the rest, like you look at this and you try to like choose the edges kind of smaller weights, right? And then see how see how you can connect the remaining vertices, right? So yeah, it's going to be this one. So 3, 5, 6, 7, 8, 9, and 15. Okay, so what's the optimal substructure here? Right? So there's an optimal substructure. Suppose you have a minimum spanning tree. Right? Suppose this is the minimum spanning tree, and there are other edges going like in this graph, but we're not showing them. So this is just the minimum spanning tree. And suppose you remove any edge. I mean, so you see the pattern of optimal substructure. Right? You look at an optimal solution and you remove something. Right? You remove any edge. Then the claim is that right now we have it's partitioned into two subtrees like T1 and T2 for these two subgraphs. So the claim is that in each part we also have a minimum spanning tree of that subgraph. Right? So the subgraph induced by the vertices of T1 and T2. Yeah, that just means like we take the vertices of T1 and then we keep all the original edges within T1, and then the same with T2. So we claim that for each part, right, each of these parts, our subtree from the optimal solution of T is also minimum spanning tree for the tree of T1 and of T2. And the proof of this is by cut and paste, right? I mean, so this kind of combining stuff, kind of optimal substructure is always by almost always by cut and paste. So what we do is, well, suppose this, right, say the for T1, like there's a better solution, right? We can use that solution and then like combine with the solution of T2 and then like paste back in the edge UV, you would get a better solution to the original problem, right? So that's what this proof is saying. And now do we have overlapping subproblems? So we do, right? I mean, we can think about like take any subset of the vertices that gives us a subproblem, and what's the minimum spanning tree of that set. But in this case, we can do better than just dynamic programming, because there's another kind of structure, another property going on that allows us to use a greedy algorithm. So the kind of property here is that a locally optimal choice is also globally optimal, right? Just like in the fractional knapsack, we can remove kind of the item with highest value per weight, or like maximum sum of the maximum weight problem. That problem, we just choose an item with the maximum weight and then look at the remaining problem. So here what we can do is, suppose we look at a tree T, right, which is a minimum spanning tree, and then we look at any subset of vertices A, right? A is a subset of the original set of vertices V, and then suppose that UV is the least weight edge that connects A to V minus A. Right? We have this least weight edge that connects the set A to the set V minus A. Then we claim that this edge UV has to belong to the minimum spanning tree. Right? So the intuition here is, okay, like we need to connect A to V minus A anyway, right? Because otherwise they're disconnected, and we don't have a minimum spanning tree. We don't even have like a spanning tree, because we need the spanning tree needs to connect everything. So in particular, it needs to connect A to V minus A. And if we need to connect them, then why not use the minimum edge weight, that minimum weight edge that connects them, right? That's the edge UV by definition. Okay, so in order to prove this, again, we can use the cut and paste, right? So suppose, remember this A is any set of any subset of the vertices, right? So maybe it's these blue vertices, right? These light blue vertices, and V minus A is this set of the red vertices. And so if you look at the, let's say like these bold kind of these non-dotted edges, so like this forms a tree, right? Suppose it's a spanning tree, and there's an edge UV, which is the least weight edge that connects the vertex of A to a vertex of V minus A. And suppose that this is not being used, kind of this edge UV, even though it's the least weight edge connecting A to V minus A, it's not being used in the minimum spanning tree. We're going to show that that's not good, right? That's a bad idea not to use this edge. So yeah, what we do is we cut and paste, right? So if we don't use this edge UV, well, I mean, there has to be some path from U to V, right? Because this minimum spanning tree has to cover the whole graph. So you consider the unique simple path, because it's a tree, right? So there's only one path on this tree that connects U to V. So currently it's this path. Right? So let me draw. It's right. This edge, and this edge. Right? So that's the path that connects U to V. So then what we do is we swap UV with the first edge on this path that connects a vertex in A to a vertex in V minus A, right? So that's going to be this edge here. That's the first edge on this path that connects a vertex in A to a vertex in V minus A, right? Connects a blue vertex to a red vertex. So we're going to swap UV with this edge, right? And we claim that that's going to give us a better solution, right? And that's because we know that UV has a lower weight than the edge that connects any other edge that connects A to V minus A, right? So if we make this swap, we're still going to have a spanning tree. So that gives us a better spanning tree, right? So a spanning tree with a lower weight. So that's why we can, for any A and V minus A, right, any partition of the vertices into these two parts, we know that the least weight edge that connects A and V minus A can be included kind of without loss of generality. So yeah, with this idea, we get to what's known as the Prim's algorithm, right? So the idea of this algorithm is that we're going to build the tree one vertex at a time, right? So we at each step we add a least weight edge from the tree to some vertex outside of the tree. Right, so at the beginning, we're going to do an example in just a second. But at the beginning, kind of, we just start with any arbitrary vertex of the graph, and then at every step, right, we're going to seek to expand this tree. Right, at the beginning, this tree is just one vertex, and then we look at the least weight edge from the tree to some vertex outside of the tree, and then we add that edge. Right, so the tree is going to grow by one vertex. We keep doing this, and we know that at every stage we can include this edge without loss of generality. Kind of, it never hurts, right? Because of our greedy choice property, we can take this tree to be the set A, and the remaining vertices, so the vertices outside of the tree, to be the set V minus A. And by our greedy choice property, we know that the least weight edge between A and V minus A can always be included in the tree. So we just include that, and then we keep going until eventually we get our tree covers all vertices, and that gives us a minimum spanning tree. Right? So this is what's going on in this code, and yeah, so it's a greedy idea, right? Building tree one vertex at a time, and at each step choosing the least weight edge. So minimizing the edge kind of never hurts here. Okay, so example. So suppose at the beginning we just include any vertex in the tree, right? So we include say this one, and now we can we look at all the vertices outside of the tree, right? So what's kind of the minimum? What's the minimum edge that connects the vertex outside the tree to a vertex in the tree, right? So it's just these three edges, because all other vertices are still not directly connected to the vertex in the tree. So the least weight edge now is 7, right? This 7. So we include this edge, and this 7 node now belongs to the tree. Now we have to update, right? So now the tree has 2 nodes, so we update kind of for other vertices outside the tree. What's the minimum cost, minimum weight connection into the tree, right? So we're going to have more connections, right? These 3 vertices have edges of weight 5, 12, and 9 into the tree. Now we know that the tree is 2 vertices, right? The 7 and 0, and so we ask, okay, what's the minimum weight edge that connects A to B minus A, right? That connects a vertex in A to a vertex in B minus A. So that's the vertex 5, right, with the edge of weight 5. So we now include this vertex, and we keep going, right? And you see that for some vertex that already has a connection, the weight can still decrease. When you look at this, the top vertex used to have a weight 12, but now with this weight 5 vertex being included in A, now there's a better connection, right? This top vertex has an edge of weight 6 to this 5 vertex, right? So this top vertex now it's updated to the 6. It used to be 12. So we make this update, and then we keep going, right? Now this 6 after the update, now it becomes the least the lowest weight connection into the tree. So we include this vertex and the 6th edge, and so on. We keep going until eventually we reach we have included all the vertices. So this 8, and then this 3 edge is now the least weight edge. So this 3 gets included, and 9 and 15, they're quite expensive, but I mean there's no choice, right? Because these are leaf vertices, so we have to include them anyway. So we'll include 9, and we'll include 15. Okay, so that's Prim's algorithm, so there's another well-known algorithm, minimum spanning tree algorithm. So it's called the Kruskal's algorithm. I'm not gonna go through that, but the idea is that so it's also a greedy algorithm, uses a kind of similar greedy approach, but slightly different. So in how it works is that at each step, so it's not gonna build the tree like one node at a time, kind of expand the tree one node at a time, like what we did with Prim's algorithm. But instead, at each step, we're gonna add a least weight edge that doesn't cause a cycle to form, right? So we look at we're gonna add one edge at a time. And of course, if an edge causes a cycle to form, there's never a reason to add that, right? Because we want a minimum spanning tree. Like if we add an edge that causes a cycle, it doesn't add any connectivity, doesn't connect two vertices that were not connected before. So we're never going to want to form a cycle. But among the edges that do not cause a cycle to form, which one do we include? Right? We claim that we can always include a least weight edge that doesn't cause a cycle to form, and that needs to be proven. So that's not immediately obvious. So you have to prove it, and that's the greedy choice property of Kruskal's algorithm. So we're gonna at each stage we look at all the edges that would not cause a cycle to form, and we choose one with the least weight. We keep going until eventually all the vertices are connected in this tree. So it's also a greedy algorithm, but it uses a different objectives, right? Instead of building the tree and then looking at the minimum weight that connects something in the tree to something outside, Kruskal's look at a global view and ask, okay, what's the next edge to be included that's the least weight edge that doesn't cause a cycle. Okay, so if you can take a look at the CLRS, so it has a section about both Kruskal's and Prim's algorithms. Okay, so any questions about these? Okay, so let me go back and answer a question about quick select. Yeah, so I mean, this is not really a point of this kind of that example, with the example of choosing the k items with the largest weight, right? So there, I said that okay, we want the and we can of course we can sort all the weights, right? Then choose the top k. That sorting all the items would take time n log n, but with because we don't really need to sort everything, right? What we want is just the top k items. So what we can do is we can if we can identify, right? Let's suppose that all the weights are distinct. But if we can identify the kth heaviest item, right? The kth largest weight, then once we do that, we can just go through all the weights and then look at which ones have higher weight than this kth highest weight, right? And these will be your k. So in order to identify just the kth highest weight, what we can use is quick select. So that was covered back in lecture 4. So that was about randomized algorithm. Remember, quick sort, like that's runs in sorting everything and runs in average case n log n time, or you can implement it as a randomized algorithm. And quick select is similar. So that's that instead of sorting everything, you just want to select any select like the kth largest element from the array of length n, and that you can do in time order n. So that's also a randomized algorithm. But yeah, again, that's not our point in this lecture. Any questions? Okay, everything clear? Okay, so then let's move on to one more example of 3D algorithms. And now this example has to do with the kind of coding data compression. Right? So it's called the Huffman code. It's actually a very famous example in this domain about kind of how you encode text and characters and so on. So what's the setting? So the settings, you have an alphabet set, right? A1 through AN. So this could be like English characters, like A, B, C, D, E, things like that. And then you have a text file. So a text file is just a sequence of alphabets, right? So this is just not your normal text file. And you want to encode this kind of using like a small number of bits, right? And now suppose you want to encode the text file with M characters, right? So what you need to do is, well, so how many bits do you need, right? So in order to, you want to change the text file into a binary coding, right? The text file, once upon a time and so on, like these are characters, but then you want to change it to like a sequence of zeros and ones. So how many bits do you need to encode this file? So if you do it kind of in a straightforward way, then you just encode each character as you make a kind of encoding for each letter in the alphabet, right? And then you use that to encode each character in the text file. So that's going to take m times like the ceiling of log base 2 of n bits, right? So that's because if you think about the binary encoding, right, you have an alphabet of size n, right? So how many bits you need to encode each letter in the alphabet? That's going to be log base 2 of n. And then you take the ceiling, right? Because that's how many bits you need to encode, kind of that's sufficient to encode n different things and different characters, right? For example, you have like 4 alphabets, right? Four letters, right? Like A, B, C, D. Then you need 2 bits, right? So with 2 bits, you can have 0, 0, 0, 1, 1, 0, and 1, 1. But if you have 5 characters, you have A, B, C, D, E. Then 2 bits would no longer be sufficient, right? You need 3 bits, because 2 bits you can only encode 4 characters. So with a fixed length coding, you can only you need with an alphabet of size n, you need the ceiling of log base 2 of n bits, right? And in order to decode, suppose you use this kind of encoding, in order to decode this fixed length binary coding, so that would be easy, right? So suppose you have yeah, let's say you have like say 16 letters, so n equals 16, and then you need 4 bits to encode each alphabet, so each letter. Then suppose you have a sequence like this, right? This is your encoding of the text, how to decode it. Then just look at each. You know that each 4 characters, each 4 bits form a character, right? Then you just look at each. You divide the sequence into like groups of 4 bits, right? And then you decode it. You look at, okay, what does 0110 correspond to, like which letter? What does 1010 correspond to, right? Which letter? And so on, 000. So it's easy to decode, right? So this works. But okay, now the question is, so can we use fewer bits to store the alphabet set, right? So answer here is no, because if the alphabet set has size n, then in any case, like to represent n different things, you need at least log base 2 of n, and then you have to take the ceiling, right? Because the number of bits has to be an integer. That you have, as I said, have four letters, right? You need 2 bits, but 5 letters, like 2 bits, no longer sufficient. You need 3 bits. But can we use fewer bits to store a file, right? The whole file, not just we're not just talking about the alphabet set, but the whole file. And for the whole file, the answer is actually yes. Like this fixed length coding is not the best option. So why is that? Yes, might seem counterintuitive, but the reason for that is that there's actually a huge variation in the frequency of alphabets in a text. If you just think about the English text, right, English characters, then there's this huge variation like there. So you can see that the letters like E and the T and these letters, they occur like very frequently, like much more frequently than some other letters like J or Q or X, something like this, right? So I mean, there's a lot of variation, and actually we can use this variation to save on the number of bits that we need, right? So what's the idea here, right? So yeah, how can we exploit the variation in the frequencies of alphabets? So the idea is that the more frequent alphabets, right? So the alphabets that appear more frequently, we should use a shorter number of bits, right? Shorter bit string, so fewer number of bits, right? Because that's going to appear more frequently, so we shouldn't waste too many bits. We should try to save on these letters like as much as possible. We should assign a small number of bits to these letters that occur more frequently. And then for the less frequent one, I mean, yeah, we don't mind too much, right? If we have to spend a lot of bits on these characters, that's fine. I mean, because they just X, like even if like the letter X, like we use many bits to represent it, but yeah, it occurs so rarely that we won't waste too much anyway. So instead of using the same number of bits to encode everything, to encode every character, we can have a variation depending on the frequency of the characters, right? Which one appears more frequently, you use fewer bits on these. Which one appear less frequently, you use more bits on these. So that's the idea, right? We're going to use a variable length encoding. Yeah, so suppose, for this example, let's say the alphabet has the letters A, B, C, D, and E, just these 5, and the frequencies are as in this table, right? So let's say A is very frequent, like 45% of the time you see the letter A, then B is 18%, C is 15%, D is 12%, and E is 10%. Yeah, suppose this is your frequency, which I mean, this kind of thing is not hard to determine, but you just take some sample text and then like look at what's the frequency. So this is one encoding that you might try. So let's say A, right, because it occurs very frequently, you want to save on it, so you just say it's 0. B occurs like a bit, it's less frequent, but still kind of frequent, so you assign it 10. C is 110, D is 101, E is 111. Okay, so I mean, this is one possibility. And then the quantity that you care about, so the quantity that you want to try to optimize in this in choosing this encoding is the average bit length, right, using this encoding. So what's that? That's defined as what kind of you might think should be defined, right? So you look at the sum over the letters in the alphabet, right, letters X, and then you look at what's the frequency of X, and then how many bits you're spending, right? How many bits you're using for this letter x, right? So that's the fx times this gamma of x. So this example, because a occurs 45% of the time, and then you use only one bit for it, so that's 0.45 times 1. B occurs 18% of the time, you use 2 bits for it, that's 0.18 times 2. And then the remaining ones, right? So C is 0.15, D is 0.12, and E is 0.1. So all these three letters, you're using 3 bits for it, right? So that's times 3, and that's going to give us 1.92, right? So that's your average bit length, and you want to minimize this, right? You want it to be as small as possible. But there's a problem with this encoding, right? Yeah, that's actually already been pointed out in the comment. Right. So what's the problem? Yeah, maybe someone haven't looked at the comments. So what's the problem with this encoding? Kind of what's wrong with it? Yeah. So yeah, the problem is overlapping prefix, right? I mean, if you see like a sequence like 0 1 0 1 0 1 1 1, you try to decode it. So you see, okay, A 0, that's A, and then okay, 1 0, that's B, 1 0, that's B again. But I mean, this is not the only possibility. I mean, you can also have 0 and then 1 0 1 is D, right? So yeah, you have more than one possibility, because these two sequences are consistent with this sequence of bits, right? A B B E and A D A E, both are correct decoding, but that's not what we want, right? We want there to be a unique answer. So this is a problem. And what's the source of this ambiguity? This is exactly the overlapping prefix, because one encoding, right? One encoding is a prefix of another, right? The encoding for B is a prefix for the encoding for D, right? The 1 0 is a prefix of 1 0 1, and that's not good, right? Because when we see 1 0, we may think, oh, it's B, but then if it's followed by 1, then we have 1 0 1. It's D, so it's not clear which one we mean, and this is what we want to avoid in our encoding scheme. Right? We don't want any encoding to be a prefix of another encoding. Right? We don't want to have something like 1 0 and also 1 0 1 for a different letter. So okay, so can we fix this? Yeah, we can do this by we can avoid having any prefix, right, being any encoding being a prefix of another, right? So in this case, like, because 1 0 is a prefix of 1 0 1, right? In order to avoid this, we add one more bit to B, right? We make it 1 0 0, and now you can see that none of the encoding is prefix of another, right? Because A is a 0, and then like B C D E, right? These all start with 1. Okay, no problem, no conflict with A, and then between B, C, D, and E, right? Among these themselves. We also don't have a problem because these are all of length 3, right? So none can be a prefix of another. So okay, so that brings us to the idea of prefix coding. So coding, like let's call it gamma of the alphabet A, is called the prefix coding if there do not exist letters like X, Y in A, such that the encoding for one letter like X is a prefix of encoding of the other letter Y, right? So that's the property that we want in our encoding. And the problem, right, the algorithmic problem is that, right, given a sequence of an alphabet, a set of an alphabets and their frequencies, we want to compute a coding such that it's a prefix coding, so no overlapping prefix, none is a prefix of another, and also minimize the average bit length. Right? So these are the two properties that we care about. Okay, so there are many possible binary codings, right? You might try to even infinite number of them, because you might even use like many bits, kind of make this coding like as long as you want. You can say, oh, letter A is 1001 1101, whatever. But I mean, of course, that's a bad idea, right? Why waste a lot of bits? So the question is, how can you choose an optimal prefix coding? right, among all these possible binary codings, right, what's the optimal one that satisfies the prefix property. So, okay, this is an idea of Huffman, and it's a very nice idea, right? So the idea is that you can convert a binary coding into a binary tree. So there's a direct correspondence between binary coding and binary tree. So what's the relation, right? What's the correspondence? So we can view this as binary tree as a labeled binary tree, where each edge is labeled with 0 or 1, right? Going down from the top, you can take the route of 0 or the route of 1. And the nodes are going to correspond to the alphabets, right? And the code of an alphabet is just you follow down the tree from the root until you reach that node of an alphabet, right? So it's the label of the path from the root to the node of that alphabet. Like this one would be like 101, this would be 1011. Okay, but that's already a problem, right? If we have like this node, these two nodes being two different letters, then you have the code like 101 and 1011. That's exactly what we wanted to avoid, right? This one encoding is a prefix of the other. So we don't want this kind of prefix. So we make only the leaf nodes correspond to the alphabet, right? Correspond to the letters in our alphabet. So these leaf nodes are the alphabets, like like A, B, C, D, E are going to be attached to these like blue squares. And the code for each alphabet is that you follow the path from the root, right? Let's say to this leftmost leaf node, the code is just gonna be 0, 0, 0, 0, right? 4 zeros. That's gonna be your code, or like the right vertex of depth 2, right? That's just 1, 1. So that's just gonna be the code. And you can see that if you just use the leaves as alphabet, then you're not going to run into a problem of prefix, right? Because now none of the leaves, right, lie on, because they're leaves, right? No two leaves lie on the same path, right? So you're going to not going to have one code being a prefix of another code. So okay, so that's good so far. So with these vertices, we can get some labelings, right? So some codes, like the leftmost is 0, 0, 0, and then we have like 0, 1, 0, 0, 1. You follow down the tree until you reach these leaves, right? But okay, so suppose you're given a prefix code, how can you build the tree, right? So suppose you're given this code that we mentioned for the 5-letter alphabet, how can you build the tree? Right, so okay, you start with the root, right? From the root, you go down the 0 path or the 1 path. Right? So the root has the 2 children, the 0 and 1, and for A, it's just 0, right? And then the remaining letters, that follows down the 1 path, right? So B, C, D, and E are here, and then the 1 path, okay, depends on whether like next is it 0 or is it the 1. So there are 2 possibilities. And then for each of these, there are again 2 possibilities, 0 or 1. So this is your tree, right? You put in B, C, D, E, and you'll see that this tree is consistent with the table, right? With your encoding, because A is just 0, and then B is 1, 0, 0, C is 1, 0, 1, and so on, right? D is 1, 1, 0, E is 1, 1, 1. This is consistent with your table. So okay, we have this correspondence. And I mean, you can also make this formal kind of this relation, right? For each prefix code of alphabet, right? We also have a binary tree and leaves, such that there's a bijective mapping, right? A 1-to-1 and onto mapping between the alphabet and the leaves. And the label of a path from root to leaf corresponds to the prefix code of the corresponding alphabet. So I mean, this is essentially what's going on in the previous slide. And now, can you express the average bit length of this encoding in terms of binary tree? So remember, the average bit length is the sum of frequency times the length of the encoding of each letter, right? So I mean, okay, so this has a direct correspondence to the tree, right? Because the number of bits you use to encode each letter is just the depth of how deep you have to go down the tree to reach the leaf node that corresponds to that letter. right? So like in the previous slide, so you see that for A, that's depth 1, right? So you use 1 bit, and then for each of B, C, D, and E, that's depth 3, right? You use 3 bits for each of them. Okay, so this gives you a formula in terms of the tree, right? Instead of the encoding. So you want to build a tree such that this average bit length is minimized. Okay, so we want to find a labeled binary tree for an optimal prefix code. Right? So suppose you look at this tree, right? This tree from the previous slides. So okay, now what's bad about this tree, right? Why is this tree clearly not optimal? Can someone identify a source of why it's not optimal? I mean, no matter, like here you don't even know the frequencies, but clearly like this is not optimal. And yeah, so for example, 0000 can, right, this leftmost vertex, this here like we can just remove it and you can make it 000, right? Or yeah, so here exactly someone is circling, right? So you can remove this node, right? So because this internal node here that has just degree 1 is just not necessary, right? It doesn't help us distinguish between any, doesn't help us distinguish between any like 2 different letters. So we can just remove it. So yeah, we can just remove this vertex, and now we have a better, a more efficient tree, right? Similarly, this one, we can remove it. So you see that for any optimal tree, it has to be the case that every internal node has degree exactly 2. Right? It cannot be that some internal node has degree 1 because that node is useless. It's just unnecessarily increasing the length of some paths. Right? So we can assume that or we know that in any optimal tree, every internal node has to have degree exactly 2, so it has to be complete, right, in that sense. So okay, I mean, well, that's good. That's a good start. But still, I mean, there are many trees. There are many such trees, right? For example, like for say like length 5, right? Alphabet of size 5. I mean, remember we saw this tree, right? So we have A here, and then like this B, C, D, E. But I mean, this is not the only possibility, right? Not the only tree where every internal node has degree exactly 2. Right? I mean, we can have something like maybe like A, B are here, and maybe like C, D, E. I mean, there's another structure, right? Another possible tree. Now, to know which one is better, right now this is not clear. There's no kind of obvious source of non-optimality in either of them. So we have to look at the frequencies now. Right. So which tree is better than which one is depends on the frequencies of the letters. So okay, we can see the influence of the frequencies on the optimal binary tree. So let's suppose we sort the alphabet, let's say like A1 through AN, in non-decreasing order of frequency. So in increasing order of frequency. So from A1 is the least frequent, AN is like the most frequent letter. Then what do we know, right? So intuitively, more frequent alphabet should be closer to the root, right? Because we want the encoding to have to be shorter, right? To have a smaller length, and less frequent alphabet should be farther from the root, right? Because we want them, we were fine with having them have them being like longer encoding because they're not going to appear that often anyway. But okay, how to organize them to achieve the best prefix code? So we're going to make some simple observations about the structure of the binary tree that should correspond to the optimal prefix codes. And these observations, they're going to be about some local structure. So this is kind of similar to in other like examples of greedy algorithm. It's going to be about some local structure, kind of what move we can make without lots of generality. What move can we make and we're sure that this move never hurts, right? Doesn't hurt. Just like we take the map, like for a fractional knapsack, we take an item with the maximum bang per buck, right, value per weight. Like you know that okay, this never hurts, or like maximizing the sum of the k heaviest weight, like heaviest items, we just take one item that's heaviest, right? You know, it never hurts, something like that. So here we're also going to make an observation about like a choice that we can always make. But and even though this choice is local, kind of it's about one move, but it's going to play an important role in the whole design of what's optimal prefix code. So okay, let's look at suppose we have this tree, right? So in the internal, we don't know what's going on, but yeah, so somewhere we have the deepest level, and there's a letter AI, and then somewhere else there's a leaf for letter A1. So remember, A1 is like the least frequent character, right? So intuitively, least frequent character should be like as deep as possible, right? Because it doesn't hurt, kind of, you know, because they don't occur that often. We're fine with having them being deep, so being corresponding to long encoding. And so suppose we have this structure, right, where AI is like at the deepest level, and that A1 is somewhere in the tree. So now, can A1 be at a shallower level than AI or not? Right. So yeah, what do you think? Can it be that like this AI is the deepest level, and A1, which is say like less frequent than AI, is at some shallower level? Yeah, if not, what's the idea of proving that this kind of thing cannot happen? Yeah, so this is a kind of a with like many greedy algorithms and ideas about like swapping, right? Kind of suppose that in the optimal solution you have something. Right? Remember, like suppose in the like for a fractional knapsack, suppose in the optimal solution you're using some items that are not optimal. We're saying that, oh, like by replacing them with better items, right? Better here means more value per weight. It doesn't hurt, right? Your solution can only get better, or with choosing maximum k weight items, right? Replacing an item by the heaviest item, it doesn't hurt. So here, like similar thing is going on, right? So suppose A1 is shallower at a shallower level than AI, then what we can do is we can swap them, right? And you'll see that it doesn't hurt because A1 is less frequent or equally frequent, so less than or equal to than AI with their frequencies. So swapping A1 with AI cannot increase the average bit length, right? I mean, this is kind of intuitively, but you can also look at this from the formula. Right? Remember the formula of the average bit length. What is it? So it's the sum. It's the sum of so sum over all like x in the alphabet, right? Of yeah, say f. Yeah, maybe let me say a. Yeah, let's say if f times the kind of length, right? This is the depth, also the depth of the leaf corresponding to x. And so, if we swap A1 with AI, so what's going to happen? So for every other letter besides A1 and AI, I mean, their terms are not going to change, right? Because their frequencies stay the same, their depth also stays the same. But the change is going to occur only in the two terms, right? The term involving A1 and the term involving AI. And we know that A1 is no more frequent than AI, right? So we know that f of A1 is less than or equal to f of AI, right? So if we swap, we make the swap, then what's going to happen is that so these terms are going to swap, right? So suppose at first that gamma of AI, right? That's like the depth of AI is less than the depth of A1. Then what you can do is consistent. Let me write the absolute value. So what you can do is you can swap them, right? You can swap these two nodes. So then like these gammas will swap, and then you look at these two terms, right? The terms that are involved, and you see, right? Then you do the algebra kind of move everything to the same side and like subtract things like that. You see that if you swap A1 and AI so that A1 becomes at the deepest level, then your average bit length will not increase, right? So you can make this this calculation. I mean, it should be intuitive in the sense that right, because A1 is no more frequent than AI, so it doesn't hurt for A1 to be as deep as possible, like or deeper than AI. And also you can like verify this formally using algebra, kind of looking at these two terms like f of A1 and gamma of A1, also FAI times gamma of AI. And then supposing that you have this non-optimal ordering where FA1 is like at most FAI, but gamma AI is less than gamma A1, then it doesn't hurt if you swap the depth of these two letters. So you can make this, you can verify this formally. And if you swap them, then okay, that's great, right? You swap them, now you know that A1 is at the deepest level. So that means that there's an optimal binary tree such that your least frequent letter, A1, is at the deepest level. So this is something that some information that you gain from the greedy observation, right, from the approach of greedy algorithm. And okay, so the next step, since the tree is, we know that it's full binary tree, where we know that there can be no internal node with degree 1, right? Every internal node has to have 2 children, right? So A1 must have a sibling, right? This parent of A1 must have another child. So yeah, suppose it's some AI, right? And this AI again must be at it must be a leaf node, right? Because we are saying that A1 is at the deepest level. So if AI were to have children, then that would be a contradiction. That A1 would not be at the deepest level. So AI is also a leaf node, so it has to correspond to some letter. Let's suppose it's AI. And now, okay, what about A2, right? So the like next least frequent next to A1. Suppose like this AI is like A10 or something. Can it be like that? So suppose that A2 is somewhere else. Like we have this situation. So AI is the sibling of A1, whereas A2 is somewhere else that's shallower, right? So again, like what do you think? What kind of move should we make here in order to show that that this situation like should not occur? Mm-hmm. Yeah, so here, right, again, like we want to show that A2, you look at, I mean, A1 is good, right? It's not at the deepest level. But between A2 and AI, right, suppose AI is like, yeah, some I greater than 2, right, like A10 or something like that. Then, no, again, it doesn't hurt to swap AI with A2, right? Because A2 is no more frequent than AI. So we want A2 to be at the like as deep as possible. So we again swap A2 with AI, right? And that is exactly the same calculation as with A1 and AI, right? We look at the two terms that are involved in the formula for the average bit length, right? And then we can show that okay, putting A2 at the deepest level will not hurt, right? So now we know that we can assume that A1 and A2 are siblings, right? And they're both at the deepest level. Okay, so the sibling of A1 can be A2, right? So yeah, we have this structure. But okay, so there's what this tells us is that there exists an optimal prefix coding in which A1 and A2 appear as siblings, right, in the corresponding binary tree. But it doesn't tell us, right, it would be inaccurate to claim that in every optimal prefix coding, A1 and A2 appear as siblings in the tree. And I mean, this is the same is true for like other greedy examples that we've looked at, right? For example, like with the fractional knapsack, it's not, but even if you take an item that has the highest value per weight ratio, what we've shown is that it doesn't hurt, right? There exists an optimal solution where you include as much as that item as possible. But maybe like there's also an optimal solution that doesn't include that item at all, right? It could be that maybe every item has the same value per weight ratio, and so you could take any item, and so if you pick just one item, it doesn't mean that that item has to be in every optimal solution, right? It just means that that item must be in some, right, optimal solution. So there exists an optimal solution that containing that item, right? Same thing with the k heaviest items. Could be that all these items, all n items have the same weight. Then optimal solution, you can just include any k items. So you just pick one item, right? You pick item 1, and you say that, oh, like in every optimal solution, right? Every optimal solution has to contain item 1. That's not true, right? Because in that, if all items have the same weight, you could just pick any k items. Maybe you pick item 2 up through k plus 1, right? You don't have to include item 1. But yeah, what we need is just that there exists, right? That this is enough, that there exists an optimal solution that contains, say, item 1. Or here with the binary tree problem, there exists an optimal prefix coding where A1 and A2 appear as siblings. And this is enough to give us a greedy algorithm, right? It shows that the greedy algorithm works because we don't have to find every optimal solution, right? We only want to find one optimal solution. So, okay. So the implication of the lemma is that we only need to focus on the binary tree in which A1 and A2 appear as siblings, and also at the deepest level of the tree, right? We can take this information and then continue. Now, okay, in this case, it's maybe not that clear how to continue, right? Unlike in the greedy, where like one step, and then okay, we take the next item, right? The next item with the next value per weight, or like the next heaviest item. So here, okay, we know that the A1 and A2 must be at, we can assume that they're at the deepest level and they're at their siblings. But then what, right? I mean, there are still many trees with the A1 and A2 at the deepest level, and also like as siblings, right? So suppose, for example, like is it has tree alphabet has size 5, so this is one possibility. Or is it I think yeah, 3, 4, 5, yeah. Or is it this one? I mean, both of these trees are consistent with the assumption that A1 and A2 are siblings, and they're at the deepest level of the tree, right? So both of these trees are consistent with what we've said so far. But maybe, right, not both of them are optimal. Right? Maybe only one of them is optimal. So we have to continue and seeing like which of these two trees is better based on the remaining frequencies. And the idea of the Huffman coding is that now, once we know A1 and A2 are siblings, we can kind of combine them. And we say that, oh, like we treat them as well as one character, and we combine the frequencies, their frequencies. So we just add them up, and then now this is one character. And then we go like kind of repeat the same process with the remaining characters. And so we go back to like this the example with A, B, C, D, E. So it was like A is like 0.45, B is something like this, 0.18, 0.15, D is 0.12, and 0.10. Right. So with this, like what we can do first is we take the two least frequent characters, so D and E, we combine them. This now has like weight 0.22. And then we take, so among the remaining frequencies, right, so now D and E are gone, it's just the combined character which has a frequency 0.22. We then look at, okay, among these 4 remaining numbers, like which 2 are the least frequent. Now it's 0.18 and 0.15, right, so we combine them. And then, okay, like now we have 3 frequencies left, like 0.45, 0.33, and 0.22. So which 2 are the least frequent? It's 0.33 and 0.22. So we combine them to 0.55. And then finally, we have just 0.45 and 0.55 left. So we combine them. So you see that this is what the tree that we actually built, right? So where A has depth 1, and then B, C, D, E has depth 3 each. Right, so this is the process, but I mean, so far we've just showed this for the 2 least frequent letters, so A1 and A2. We haven't shown anything about the continuation of this process. But the idea is essentially the same kind of. So I'll leave this to for you to look at in CRS if you're interested in looking at how this argument continues. So, I mean, this is kind of a start, and then kind of we make same greedy argument that in the next step is also the best idea to look at the two characters with the least frequency. So okay, so that's the idea of the Huffman code, right? We want to build the optimal encoding of any set of any alphabet based on the frequencies of the letter, and we can do better than the fixed length encoding. So we use variable length encoding, and underlying idea is the greedy idea that the least frequent characters we can just combine, like put them in the deep level, and then kind of build up the tree by combining these frequencies from bottom to top, from least frequent to most frequent. And yeah, so that's it for this lecture. So in the next, right, so we have only 2 lectures remaining. In the remaining 2 lectures, we're going to look at the reductions and intractability, so kind of complexity of hard problems. Okay, so yeah, that's it for this week, and see you next week. I'll stick around for questions. Okay, so does the knapsack problem prove that the optimal choice must contain the item with max value per kilogram instead of there exists an optimal choice with the max value per kilogram? Yeah, I mean, so the thing is, it could be that all items might have the same like value per kilogram, right? So yeah, so actually, what the argument shows is that it must contain an item. Yeah, I think this is an important distinction. It must contain an item, not the item, right? Because there might be many such items. It must contain an item with the max value per kilogram. Now, if you assume that all items have different ratio of value per kilogram, then indeed, like it's true that the argument would show that you have to go by from maximum value per kilogram to minimum. You have to take first like the item with the maximum value per kilogram, like take the whole of this item or as much as possible, and so on. But yeah, when I say that kind of there exists a solution, I try to be careful about having ties between items with the same value per kilogram, or like in this binary tree problem, kind of want to be careful about. Okay, it could be that many letters have the same frequency, but if you assume that say all letters have different frequencies, then it would be true that you should not put something like A1 not at the bottom level and like some other letter at the bottom level. Right? Then in that case, a swap would be a strict improvement. Okay, can you explain again why we could swap leaf node at the different level? Yeah, so let's take a look at that. Yeah, so here, right, what we want to do is we want to swap A1 and AI, right? We're saying, okay, like at the moment, suppose the A1 is less, right? So suppose A1 is less frequent than AI. Let's say, yeah, maybe let me assume, yeah, maybe it doesn't matter. Yeah, let's assume weak inequality, like frequency of A1 less than AI, but but A1 is at the shallower level than AI, right? So gamma of A1, let's say it's yeah, less than, yeah, let me not write absolute value, but yeah, this gamma currently just means the length of the encoding. So that also corresponds to the depth of the leaf, right? So gamma A1, gamma AI. So if we look at the relevant terms in the right, ABL, right, average bit length formula. So remember, it's sum of like f of x times gamma of x, right? So currently, what we have is the f of A1 times gamma of A1, and then plus f AI times gamma AI, right? This is the relevant terms, because the other terms, like for A2, A3, for every other term that's not A1 or AI, like even if we swap A1 and AI, these do not change, right? So now, like suppose we swap A1 and AI, right? What's going to happen? But how do these terms change? Right? It's going to be FA1, it stays the same, right? But now A1 takes the place of AI, so it now takes like the depth of AI, and so it's like old ABL, old average bit length, and then the new average bit length is going to be FA1 times gamma of AI plus F of AI times gamma of A1, right? So we care about these two quantities. We want to show that if we make the swap, then it's going to be better, right? The new ABL is going to be better than the old ABL. So that means like old, what we want to show, right here, the old minus new ABL, right? We want to show that it's non-negative, right? So that would mean that the new ABL is at least as good as the old ABL, because we want to minimize the ABL, right? So now what is old minus new? Right? So it's FA1 gamma A1 plus FAI, right? So this is the algebra that I was referring to, that you can show this algebraically. FA1 gamma A1 plus FAI gamma AI. So this is the old ABL, right? These two relevant terms. So I just, because other terms like A2, A3, other terms like just the same in the old and new, so we can cancel them. And then we subtract the new, right? So it's minus FA1 gamma AI, and then minus FAI gamma A1. Yeah, we want to show that this is at least 0, right? So now, okay, you can see that this term factors, right? So, I mean, this is a pretty standard argument with the greedy algorithm. So we just look at the make a swap, and then we show that the swap kind of leads to something better. So here we have FA1 minus minus FAI, and then gamma A1 minus gamma AI is what we want to show, right? At least 0. Now, why is this true? I mean, well, this we can just use the assumptions, right? So because we have the assumptions here, that FA1 is at most FAI, and gamma A1 is say like no more than or less than gamma AI. So then we know that this term is what FA1 minus FAI is like less than 0. Gamma A1 minus AI is also like less than 0. So something non-negative or non-positive, like two terms like this multiply with each other, then it has to be at least 0, right? So we know that with the swap, the ABL does not increase, right? The swap between A1 and AI, and so we can make this swap without loss of generality. Kind of, we can assume that A1 is at the deepest level by swapping with, if it's not at the deepest level, swapping it with something at the deepest level does not increase the ABL. Okay, so decoding, we would just go like for a string of alphabet. Decoding would mean you're given a string of bits, and then you want to like get back to the alphabets. Yeah, so what you can do, right, is that one way, like way to do it would be just traverse the binary tree, and then you're given a bit like 0, 1, 1, 1. You just follow down the tree until eventually you reach a leaf node, and that would be your next character, and then you keep going. Or yeah, I mean exactly. You can also make a lookup table, so either way would be fine.